My name is John Wynn, and this is my colleague John Guyver, and we're going to be talking about Infer.net and building software with intelligence. And Infer.net is a project that we've been working on over in Microsoft Research in Cambridge in England. So the idea behind this project is that we want to make it easier to write software that can adapt, that can learn, and that can reason about, well, about whatever. So let's look at some examples. A simple example is if we have someone using a stylus to write on a tablet, we might want to be able to adapt to the way a particular user writes that word so we can work out what it is they're trying to say. Or in another example, if we have a lot of people using a search engine, we'd like to be able to learn what search results people are finding useful when they type in a particular query. In another example, if we have a whole lot of people playing an online game like Halo 3, we'd like to be able to work out who's the best at this game. So we'd like to be able to reason about skills of the players based on their performance. So these are some examples, and we're going to be looking about how we can write software to achieve these kinds of intelligent tasks. Now, all of these intelligent tasks have something in common, which is that the thing that we're trying to work out, the word, the search result, or the skill of the player, is not something that we can directly measure. Instead, what we actually get to measure is something like the gestures that are made with the stylus, or the clicks that the users actually give on the search results page, or in the case of the game, the results of a number of games. And the challenge in all of these tasks is to take the things that we measure and to reason backwards to things that we can't measure. So going from the gestures backwards to the word, the clicks back to the preferred search result, or from the game results back to working out who's the best. Now, at the minute, when we do this, it's possible that there are multiple possible explanations for a particular measurement. And it's very important that we capture that uncertainty when we're handling this reasoning backwards task. And so we work with probabilities here to cope with the fact that there is this uncertainty in the causes of a particular measurement. So going back to our example with the stylus, if someone writes a sequence of gestures on a tablet, it's very possible that there are multiple interpretations of those gestures depending on how bad your handwriting is. So if you try to write hello, it might be most likely that that was the word, but there might be a possibility that you could interpret the gestures as halo or hall or many other words. So when we're doing these intelligent reasoning backwards tasks, it's really important that we incorporate probability at a fundamental level. So how is this done at the moment? There are a number of bits of software out there in the world which do these kinds of reasoning backwards tasks, whether that's speech recognition, handwriting recognition, or things like spam filters. And the way it's done at the moment is it's laboriously coded by hand in a standard programming language. And this is going to typically take a long time to set up and hundreds or thousands of lines of code to solve these kinds of complex problems. So what we're going to talk about today is a new approach to doing these intelligent tasks, which we call probabilistic programming, where instead of writing in a standard language, we write a much shorter program, a probabilistic program, using the Infer.net tool. And typically, this program will look like a forward simulation of the system that we're trying to reason about. And it's going to be a much shorter thing, maybe 20 or 30 lines of code. And the result is that when we want to solve these intelligent reasoning backwards tasks, we're going to be able to do it in hours instead of months. So just to give you a flavor of what we can achieve with this, before I get down into the details of what a probabilistic program is, I'm going to talk about some things that people have already been using this tool for, and maybe get you excited about what it's for. So we've had people use it for in social networking. They've had some data of a social network, a friend graph, and information about the musical tastes of each of the people in that graph. And by using a probabilistic program, they build a simulation of how music recommendations and music tastes flow through that social network. And then you can use that to recommend songs to people in the social network, or to identify communities of users who are interested in the same kind of thing. In a very different application, we've had some researchers working on health epidemiology who've been looking at electronic health records, in this case of 1,000 children. And they built a little simulation which is trying to work out how children get asthma. And by building the simulation and doing backwards reasoning from the health information, they're able to get new understandings of the causes of asthma. So these are two very different uses of this kind of technology. And indeed, there are many more. I'm not going to go through all of these in detail, but people have used these probabilistic programs for everything from program verification and security, movie recommendation, checking of online forms, calibrating of judgments of web pages, even extracting the plots of books automatically so that you can visualize the plot. So there's lots of fun things that you can do with this kind of tool. So having told you all the exciting things that you can do, I'm now going to go to the most simple possible probabilistic program that you can imagine. So this is like the hello world of probabilistic programming. And I'm afraid it involves coins. So it's kind of essential for probability to mention some coins, so we're going to do that. So I want you to imagine the situation. I have two fair coins, and I'm going to toss them. And the question that we're going to start off with is, what is the probability that both of these coins are heads? Well, I'm sure you can all know the answer to that, which is a quarter. But let's look at a probabilistic program to work this out. So in fact, the first probabilistic program I'm going to show you is just going to be in C#, plain C#, just to give you some idea. So in the first line here, I'm going to create a Boolean variable which has a 50% chance of being true. So random next double gives you a uniform random number between 0 and 1, and testing if it's greater than 0.5 means there's a 50% chance of true, 50% chance of false. So if we execute this line, then we might get, for example, true as being the value of first coin. Second coin is flipped in exactly the same way. This time we get false. And then if we want to work out whether they're both heads, well, if true is heads, then we can do that by saying first coin and second coin, right? And so in this case, that's false. We can run this program again, and because it's a random program, we'll get some different set of results. Run it again, different set of results, and so on. Now, if we run this program a really large number of times, say 1 million times, then we can start to count the number of times that each variable is true and false. So if we do that, what we find is, as we would expect, the coins are fair. So first coin and second coin are true 50% of the time, roughly. And both heads is going to be true a quarter of the time. And so we've answered our question, which is the answer is a quarter. But so far I haven't talked about how we can do reasoning backwards. So let's look at a reasoning backwards problem with the coins. So in this situation, I want you to imagine that somebody else tossed 2 coins secretly, and they told you that they didn't get 2 heads. Okay? So they might have got no heads or 1 head, but they didn't get 2 heads. That's the information you have. And the new question is, what is the probability that the first coin was heads? Now this is a more, already we're getting into a sort of non-obvious answer. I can tell you the answer is a third, and maybe you can work that one out. So there's 3 possibilities that they got tails, tails, heads, tails, and tails, heads, and only one of those has the first coin being heads, so 1 out of 3 is a third. So how can we use our probabilistic program to answer this reasoning backwards question? Well, the program stays the same, but now we add at the end this observation that both heads is false. And we again run the program a large number of times, but now we throw away all the runs of the program where the outcome didn't match our observation. So we throw away all the runs where both heads was true. Now if we run the program 1,000,000 times, we'll get a different answer, which shows this reasoning backwards property. So I'll actually run this in C#, just so we get some Visual Studio time. So I've written a really simple C# program. Here you can see the probabilistic program you just saw. And then, excuse me. And then all we do is run that 1,000,000 times here and print out the proportions of times that first coin is true and that both heads is true. Okay? So very simply. Now this is without observations, and we get the first result, which is that first coin is true 50% of the time, both heads is true 25% of the time. Now if I add in the observation, I do this by throwing out all of the runs which didn't match our observation. So if both heads is not false, then we're not going to count that. And if I run it again, then we get the answer that the first coin is true 33% of the time, and that both heads is true never, because we observed that it was false. So this is a really simple example of reasoning backwards, achieved by running a C# program 1,000,000 times. And so that was our answer, 1/3. But this is not a practical way of doing reasoning backwards. In fact, I showed it to you mainly to illustrate the concept of a probabilistic program. If we want to reason about a real-life situation, then there's not going to be 2 variables involved or 3 variables. There's going to be thousands of variables, maybe corresponding to the players of a game or whatever. And even if we just had 20, then we might need 2 to the 20 million runs to get some idea of the probabilities involved. So this is not a practical approach to reasoning backwards. And so we provided this tool to do just that, to provide a practical approach to reasoning backwards. So how did that work? So let's look at the coins example again, but this time using Infer.net. So the first thing to note is that Infer.net doesn't work by taking 1,000,000 runs and saying half of them were true and half of them were false. Instead, it works with probability distributions. So it can have values that are 50% true and 50% false. So on this first line, we're going to say that the first coin has this distribution value. So it's both true and false with equal probability. Okay? Now, the name for that distribution, the mathematical name is Bernoulli, which is why in Infer.net you create that by saying variable Bernoulli 0.5, and the 0.5 is the probability of true. Okay? So we create a second coin variable the same way. Now, when these variables don't have fixed values like true or false, but have these uncertain values, like 50% true, 50% false, we call them random variables, random or uncertain variables. Okay? Now, in the third line, we're again creating the both heads variable. And because it's a function of random variables, it is also a random variable. And its distribution will be another Bernoulli, but with a probability of 25% of being true. But we don't know that. We've specified the distributions of first coin and second coin, but the distribution of both heads is now implicit within the program. And we need to get that distribution out of that random variable. And this is called inference. And this is what Infer.net is all about. So to get that distribution out, we use something called an inference engine. An inference engine is a heavyweight bit of mathematical software that can look at your random variable and determine what its distribution is. So in this code, the first line we create an Infer.net inference engine. And on the second line, we ask it to give us the distribution for the both heads variable. And we say, give me a Bernoulli distribution. And that's now not a random variable, that's just a distribution object of type Bernoulli. And we can ask that object, what is your probability of being true? So on the bottom line, we do that, and the result is now exactly a quarter. So we haven't had to do 1,000,000 runs, we've done one run, and we've got exactly the right answer. But what about reasoning backwards? Well, if we want to add an observation, then we just take that random variable both heads, and it has a property observed value that we can set if we want to say that we knew what its result was. So if we say that both heads is false, then we say both heads observed value equals false. Then we take the inference engine again, and now we infer the distribution over the first coin. And because we made that observation, that actually had a backwards effect through the program and modified the distribution of first coin. And so now it has a probability of 1/3. Okay? So let's look at that in Visual Studio. So I'm just going to switch over to the Visual Studio project using Infer.net. And all we do to use Infer.net is you need to add 2 references to the libraries that we provide, the compiler and the runtime. Then you can import these Microsoft Research Infer namespaces. Here we have our probabilistic program. Here we create the inference engine. And then we solve the first question, what's the probability of 2 heads? And print it out. And then we add our observation, and now we're doing backwards reasoning and printing out the probability of first coin. So if we run this, we now see that we get the exact answer, 25% and 1/3. Okay, so I want to just explain a little bit about how Infer.net works. So the first thing that's different when Infer.net is executing is obviously it's working with distributions rather than values. And so when we assign Bernoulli 0.5 to first coin, that distribution value is being placed into the first coin variable. That's quite straightforward. The same is true of second coin. And then when we compute the AND of the two, that distribution goes into both heads. Excuse me. But now we come to a crucial difference between Infer.net and an ordinary program, which is that it can execute both forwards and backwards. So not only does the information flow forwards through the program, but you can also send it backwards by using backwards messages. So when you do an observation, like saying both heads is false, this is actually a backwards message to the both heads variable that says you are false. And as I said, that information then propagates upwards through the program. So it goes up to the AND, and then up to the first coin and second coin variables, modifying their distributions. So this is a funky difference between a probabilistic program and an ordinary program. In a probabilistic program, information flows forwards and backwards through the program until all of the distributions that you need have been calculated. So I want to move on from coins to some real applications, but we've got to do one more thing with them before we do that. But when I say tossing a coin, it might help motivate it if you think about, say, clicking on a link on a website, or choosing a menu option, or maybe buying a product. All of these are events that can happen or not happen that we can use these tools with. But when we're interested in those kinds of events, we're interested in whether they happen or whether they don't happen, but we're also interested in the probability that they will happen. And this is like having a biased coin, a coin which is no longer fair. And so now I'm going to show how we can use the same ideas, same probabilistic programming ideas, to learn the bias of a coin. So the bias of a coin is controlled by the probability of heads, which we'll call P. And let's suppose for a moment that P is actually 50%, so the coin is fair. If I toss that coin several times, so we get a sequence of outcomes, then I might get true, true, false, false, true, false. So that's the sort of sequence I would expect to get from a fair coin. If the probability of heads is more like 10%, then I'd expect to get this sequence on the left, where there's many more falses than trues. If, on the other hand, it's more like 90%, then I'd expect to get that sequence on the right, where it's more trues than false. That's straightforward. But now let's think about reasoning backwards. Supposing you saw the sequence of outcomes in the middle. So you saw this sequence of heads and tails, trues and false. Does that mean that you know the coin is fair? Well, it doesn't. It could be that the coin is, say, 45% probability of heads or 55% probability of heads. All this sequence tells you is that it's more likely to be closer to being a fair coin than an extremely biased one. All right? And we can express that using a distribution like this. So this orange curve is showing the probability that the bias is various values. And it's now got a hump around 50% that says, after seeing these 6 coins, it's more likely that my coin has its probability of heads around 50%. If I'd seen the left-hand sequence with many more tails than heads, then that doesn't tell me that the probability is 10%, but it just shifts my expectations towards a low probability of heads. So we get a different curve that looks like this, pushed to the left. And if I see the sequence on the right, I get a different curve now pushed to the right. So these are probability distributions, not over true or false, but over a double value between 0 and 1. And we call these distributions beta distributions, because we're mathematicians and we like to use Greek. Now, you can use beta distributions just like we were using Bernoulli distributions before in Infer.net. So here is the code to work out the bias of a coin given a sequence of tosses. In the first line, we are creating a random variable again. This time it's a random double variable, which has a beta distribution which is initially flat. So we're just going to, this is a flat, so beta 1, 1 is just a flat distribution, uniform between 0 and 1. And then we have our sequence of tosses. And when we create these Bernoulli variables now, instead of putting in 0.5, we can put in P, this unknown beta distributed probability. And then we observe that the outcome of the first toss, maybe it was false, and in the second toss we create exactly the same way. Now we observe it's true, and so on for some sequence. And then when we get to the end, we can now say, okay, use my inference engine, infer the new distribution over P. What's that going to be? And what you'll end up with is these curves like you saw on the previous slide based on what the sequence of tosses was. So it might be biased towards the left, the right, or the middle. So we can use exactly the same reasoning backwards ideas to reason about these curve-type distributions over continuous values as distributions over Boolean variables. So now I'm going to hand over to my colleague, John Guyver, who's going to show you how you can use these two types of inference to solve some fun, real applications.
Thank you, John.
Yeah, there's a question.
Is there a way to say, once you said the value of a coin flip, go back and say it's undecided and does it reason backward to the previous state?
Okay, so the question is it possible to undo an observation effectively? And yeah, absolutely. We have, I think it's called clear observed value, and you can do exactly that. Okay, I'll hand over.
Okay, so I'm going to look at a couple of sort of more realistic examples. And first example I'm going to look at is in the area of search engine log analysis. And this is a particularly good example to follow on from what John was talking about, because it uses exactly the same probabilistic program elements as we saw in the various Hello World examples that John was talking about. So we assume a user enters a query into a search engine and hits enter, and we get a page of results back. And then the user starts interacting with that page of results. So the first thing the user will do is they'll look at the sort of summary information, the snippet information for the different items on the page. And then they may click, say, on the first document here and go and look at that document. And then maybe they'll navigate back to the results page. And maybe they'll skip over the second document, and then maybe click on the third document, and then maybe exit at that point. So that interaction that the user has with the results page is captured in a click log, a log of true and falses, which is associated with that result page and that query. Right, so now what we'd like to do now is, within this situation, is reason backwards from those observations. So we observe clicks. What we'd like to do is reason back as to the quality of the results page, how well it sort of satisfies a user's information needs. So now, probably not many of you, if any of you, are building search engines, but this type of analysis and the type of ideas inherent in this example can equally be applied to a web application where you're interested in learning and understanding how your user navigates through that web application with a view to improving how you present information in that web application. So we want to write a probabilistic program, and to help us do this, this flow diagram here represents how a user might navigate through our page of results. And let's look at our user. Okay, here he is on the right. And we're going to put ourselves in the mind of this user. And as we go through this flow chart, we're going to be writing our probabilistic program. And you'll see little snippets down in the right-hand corner as we get to the appropriate points. So the first thing the user does is he examines the summary information, the snippet of information. And we're going to assume that the user starts looking at the top result and then works his way down. So the user has to decide, am I going to click on this item? So now he's going to click on the item if he finds the summary information appealing. Does it match what he thinks his information need is? So we can imagine a variable, an appeal variable, which is sort of an underlying appeal of this summary information relative to the query. And we can imagine a population of users, and some may find it appealing and some may not find it appealing. Okay? But if the underlying appeal is high, then most users will click. And if the underlying appeal is low, then most users will pass over that item. So that appeal is like the bias we saw in the coins problem. Okay? It's not something we know. It's something we want to infer. But we specify it as a variable, as a random variable in our problem. And then that becomes the bias, the unknown bias of a coin flip. And you see the little bit of code down in the right-hand corner. That's the Infer.net code for a coin flip, where the appeal is now the bias. So let's see what our user does. He decides, yes, it's promising. Let's click on that link, and we'll view the document. Okay, at this point, he's looking at the document, and he's deciding, is this document relevant to my information need? And we can consider this in the same way as the appeal. We can imagine that there's an underlying relevance, and we can imagine a population of users, And if the underlying relevance is high, then most users will find it relevant. If it's low, then most users won't. But it's still an uncertain, it's still an uncertainty as to whether a particular user will find it relevant or not. So that, again, is a coin flip. So now relevance, this unknown relevance, is a random variable that is the bias for another coin flip. So let's flip the coin. And a user doesn't like this document. So then the next thing he has to do is decide, well, am I going on to look at the next document, the next item in the list? Am I going to look at the next summary item in the list? Okay, well, as you can already probably guess, this is another flip of a coin. Now here, I've hard-coded this to be 0.9, but this could also be a random variable. So here, the reason I've encoded it to be 0.9 is that if someone has not found a relevant document, they're more likely to go and look at the next document on the list. So that is heavily biased towards examining the next item on the list. So we'll flip that coin, and it comes out heads. So he goes and examines the next item on the list. And now we just repeat the process. Okay, the second item on the list has a certain appeal relative to the query. That appeal is the bias. We flip that coin. Yes, he decides to look at that document. Okay, is it relevant or not? Well, we flip the relevance coin, and now that relevance is for that document relative to that query. And in this case, our user is happy. But even if he's happy, he still might, with some probability, go on and look at the next item in the list. But this will likely to be a lower probability. And again, I've hard-coded this, but it could also be a random variable in the problem. And we flip that coin, and in this case, he's decided he's got the information need, he's fulfilled his information need, and he quits. So what we'd like to do now is we'd like to reason backwards about the relevance and the appeal. Well, first of all, let's just look at a couple more snippets of Infer.net code that we use to create this sort of forward simulation of the user interacting with the results page. So this first statement, this examine variable is a random variable which says, is the user examining the snippet at position D? And if we just go back and look at our flow chart, this is the variable that corresponds to the examine box there. Okay, and to get to that examine box, there are several routes through the flow chart to get there. And this statement here just shows the logic. It's a set of logical operations which just reflect that path through the flow chart. And then the click variable is whether the user has clicked at the item in a particular position. And first of all, the item has to be examining that snippet. And then they have to flip the coin. And if it comes out heads, then if both of those are true, then click will be true. And similar with whether the user finds the document relevant. Okay. Now, to reason backwards, we need to pin observations to this model, because to this program. Because what I've shown you so far is a program which has no data, no observations. It just reflects a process of a user interacting with a page of results. But we have the click logs now. This is where the click logs come in. So each column in the click log is a record of an individual user on a specific query interacting with a page of results. And we pin a record to our random variables using the same observed value mechanism that John's already talked about. Okay, so what I want to do now is actually run this program. And so we've sort of built, there we go. We've built this sort of forward simulation. Now the question is, does it really give us something that's intuitive when we reason backwards. Okay, so we're going to do a very simple simulation of running this program. Where we're just going to look at the first 2 documents in the list rather than 10 documents in the list. And we're just going to make inference about the very first document in the list. So on the right-hand side, you see the 4 possible outcomes of interacting with 2 documents. So true is click on the first, click on the second. True, false is click on the first, don't click on the second, etc. And we're going to assume that there are no clicks below that, just to see if this matches our intuition. And the slider bars are the number of users associated with each outcome. Okay, so we'll do some simple experiments here. So let's look at a situation where there are a bunch of users who click on the first and then click on the second, and none of the other outcomes are observed at all. Well, what we expect to see here is that everyone's clicking on the first document, so we expect the summary to be really good. But everyone's also then clicking on the second document. So their information need has not been satisfied by the first document. So we expect that the relevance of the first document to be really bad. And you see in the middle there, the appeal and the relevance bars, that appeal is very high and relevance is very low. So this certainly matches our intuition for this simple situation. And now if we look at the second outcome in isolation, so we have a bunch of users clicking on the first document and none of them clicking on the second document after they've clicked on the first, we see that both the appeal and the relevance of the first document are strong. And that's, again, as we'd sort of expect. Because no one's gone on to click on the second link, their information need has been satisfied by the first link. And we can look at the third outcome. And here we see that everyone is skipping over the first link. And what that suggests is that the snippet of information, the summary information, is really poor. No one wants to click on it. Okay? And that's reflected in the results of the inference. But we can't really say anything about relevance because no one's actually looked at that document. So the relevance just sort of sits there in the middle. We can't really draw any conclusion about it. Okay, so now you're probably thinking, well, this is simple logic. I could just hard code this up. And that's true in this simple case. But when you start to look at combinations of different users doing different things, and when you have all 10 documents in the list, that logic becomes very hard both to specify and to maintain. But it's an effortless result of inference in our simulation model with Infer.net. Okay, so let's close that. And so here's the code. We've already looked at some of it. This is slightly different from what you saw on the slides because there's a user variable in here, a user index in here now. But there are a couple of items I just want to draw to your attention. One is this for each statement. So within a probabilistic program, you'll also often be dealing with large arrays, possibly irregular, jagged arrays of data. And you'll have array random variables of different sizes and shapes. And the value of the for each statement is that it does inference on those array type situations and sparse arrays and very large arrays. It does it very efficiently. Even more interesting is the if statement and its associated if not, which you can think of as an else. Unlike a deterministic program, in an if-else, only one of the 2 blocks in an if-else is executed, depending on the value of the conditional expression in the if statement. In a probabilistic program, both the if and the else are executed with some probability. And actually, the mathematics behind that is quite sophisticated. And when you hit the infer, there's a lot of machinations that go on behind the scenes to actually allow those types of expression to be executed. Okay, so let's get back to our talk. Okay, so here's the second example. So how good at Halo are you? And why should we care? Okay, I mean, one thing's probably for sure, you're all better than I am, seeing as I don't play it. But there are millions of games played every day, and of Xbox Live games. And one of the key things you need to do is you need to match up players in teams or in individual free-for-alls that are reasonably similarly matched. So teams should be similarly matched, individual players should be similarly matched. So the games are relevant and interesting. And there's a system called TrueSkill, which has been around for a couple of years, that actually came out of the same lab that we're from, that uses inference to do this. And just the inference algorithm itself took several months and many lines of code to implement. And we're going to show Infer.net code for this, which is just a few lines long and can be done in an hour. So what's happening with TrueSkill is that at any one time, there's every player has a skill profile that is maintained by Xbox Live. And then we observe games. So here we're seeing a free-for-all between 3 players, Sully, Sniper Eye, Dr. Slowplay. And that game has an output, has an outcome. So in this case, Sully scored 25 kills, Sniper Eye 22, Dr. Slowplay 17. And so Sully came out on top. We have a rank 1, 2, 3 in that order. And it's the combination of the old skills and the outcome of games that are used to update the new player's skills. So let's look at how that works. So now these are, we've seen Bernoulli and beta distributions. Here we're using Gaussian distributions, which you're all familiar with, but perhaps haven't seen within an inference setting. And the skills are represented by these distributions. So each player's skill is maintained as a Gaussian distribution, which has a center or mean and a width or standard deviation. And here we see that Sniper Eye has a very sort of narrow, tall distribution. And what that says is that we're very certain about his skill. His skill is pretty much 30, plus or minus some uncertainty. Whereas Sully is at the opposite end of the scale. Here we're very uncertain about Sully's skill. There's a very wide range of skills that he could actually be. So now what we've seen in this outcome is we've seen that Sully has beaten Sniper Eye. And so we expect his skill to increase. And so if we here. Oops. Sorry, I'm getting a little bit. Okay, this animation seems to have been doesn't seem to be coming through. So what you should see here, and I apologize for this, what you should see here is that as after they've played, Sully's distribution will get narrower and shift to the right. And Sniper Eye's, and so we get more confident about his skill level. We're still uncertain about it. Whereas Sniper Eye's shifts a little bit to the left, but only a very small amount because we're already very confident of his skill level. So here's the Infer.net program for this. So we have an old skill represented by an old mean and an old standard deviation. So center value and width. And skill 1, skill 2, and skill 3 are the random variables which are distributed according to those Gaussian distributions. So these are random variables. Now, when a player plays, they're going to, may have a good day or they may have a bad day. So there's some randomness in performance as well. So whatever their skill level is, their uncertain skill level is, there's also an uncertainty in the performance. And that's reflected by these lines 4 through 6, the performance lines, which say that there's also uncertainty that represented by this beta parameter. And now to reason backwards, we have to pin observations to our model. And we've seen how to do that with observed value. And these constrain positive, in this situation, just a shortcut for a couple of lines of code which say create a random variable perf1 minus perf2, which is the difference between two performance levels, and then constrain that random variable, observe that random variable, create a Boolean variable which says that the difference between performances is greater than 0, and then observe that value to be true. So this constraint positive does those 3 lines in one. And then we're constraining performance 2 to be greater than performance 3. And then we're calling infer. And behind the scenes, infer does the reasoning backwards, and we get the updated skills. So that's just a few lines of code. It's an hour's work, and it implements TrueSkill. Sorry, was there a question? Sorry, I did that again. I keep on hitting end here. Okay.
The outcomes, the constraints, constraint positive.
Right.
1 minus
Okay, you want me to explain that again? Okay, so perf1 and perf2 are random variables. Okay, perf1 minus perf2 is another random variable. Okay. To do it in longhand, we'd create another Boolean random variable, which is perf1 minus perf2 greater than 0, right, with a logical expression. Okay, and that would then be a Boolean, a true-false type random variable. And then we'd say, now we observe this to be true. And so that 3 lines of code would say we observe perf1 to be greater than perf2. So this constraint positive is just a shorthand for those 3 lines.
That part I understand, but I don't understand why that constraint is there.
The constraint is there is because it's the observation that the top-ranked player beat the second-ranked player. Yeah, so that's the observation that we have, is the performance, the outcome of a game. Okay, so we've looked at some probabilistic programs in Infer.net. We've looked, and this is sort of a page which really summarizes some of the language elements of these probabilistic programs. So we've seen various distributions. We've seen Bernoulli, we've seen Gaussian, we've seen beta. There are several other distributions, and they all have sort of important uses for describing probabilistic types of program. So for example, if instead of flipping a coin, you wanted to roll dice instead, okay, you'd use a discrete distribution. Now, we've also talked about the if statements, the if not, the for each statements. There are also switch statements and case statements. And then there are also elements in Infer.net for constructing new random variables out of old random variables. So if you look down at the bottom left, we have A is a Boolean random variable that is constructed from the expression B greater than C. And up to this point in what we've been showing, we've been using just implicit typing for the random variables, but in fact these are generic types of type variable over whatever domain the random variable is.
May I ask one other quick
Yeah.
What if you don't know the underlying distribution? It could be exponential, it could be Gaussian, and you're not sure. You don't know enough about the population.
Well, I mean, that's a very good question. Well, typically, there are sort of standard ways of putting models together, depending on what you want to achieve. And the distributions that you specify for different variables are chosen to be, essentially to be tractable, to do large-scale inference.
So you have to basically know that much at least to build the model. It won't back into that as well.
No, I mean, there is a little bit of expertise. I mean, we have lots of examples to be able to do that, but there's a little bit of expertise and sort of, experience of sort of usage to understand those things. And there are lots of sort of, canonical examples that we provide for different types of situation.
Can I add one point to that, John? So you can actually, if you want to work out, if you don't know which of several distributions to use for a particular variable, you can actually use something like the if construct, variable if here. And you can try both models at once. So you can use the if statement, and in the if block, you can create the variable one way. And in the else block, you can create the variable the other way. And then when you attach data, you can then infer which of these two blocks was more likely given the data, and that will tell you which distribution to use, which type of distribution to use. So the if statement is really powerful for that kind of thing.
So it would infer the probability that it's this distribution versus this.
Exactly. It's not a hard choice, but it's a probability.
Okay. So we looked at some of the elements of the Infer.net programming interface. So we've seen how to construct random variables. We've seen how to pin data to these random variables through observed value. We've seen about inference engines, and we've seen about the infer method. Now, what happens when that infer method gets called is actually that the program we've described, the probabilistic program, gets compiled into an efficient algorithm. So there's a sort of a back-end compiler step that takes place when you run infer. And that's what gives great scalability and a performance to the Infer.net inference. Now, where we'd like to go at some point is to, again, this animation is not working. I don't know. Sorry again. We were told, actually, just before this talk, that this is a room with gremlins. That something happens every morning. So this must be the gremlin. Ah, there we go. Okay, so what we'd like to go is, what we'd like to do is we'd like to take these API constructs and actually have them as an integral part of high-level language. So random variables, i.e. variables which can take on a number of different values with some distribution, are actually part of the language. And we already have the back-end compiler to this, so it's not actually a huge step to think about doing this type of thing. Okay, and let's conclude with just a plug for the website where you can download Infer.net. It's a pre-download. We put it up December last year, so it's been up close to a year now. We've had a lot of downloads, there's a good community, a community forum, a lot of discussion, a lot of people doing a lot of different things. And there's also tutorials and user guides and so on there. So I really encourage you to download it and play around with it and think how you might use it in your applications. So with that, I'm going to say thank you again for coming out at 8:30 and throw the floor open to questions. We've got 5 minutes for questions. Yeah.
When you were doing your analysis of the tweaks on the website,
Yeah.
account which link was clicked first, just whether it was clicked or not.
Yeah.
But when you talked about click first and click second. And I wondered if the real inference takes that into account, and how would that modify the model?
Well, so the program that we built had certain assumptions, and the assumptions were that a user will go down the list in order. Okay, and that was the assumptions for this program. Now, you could conceive a more complex program where you try and model the order things are done in, and the nice thing about this type of inference approach is that you can add in all the variables and conditions you think actually reflect the real world. So you should use the real world knowledge you have about your domain, and this might come from user studies, for example, or other sources of information, fundamental information that you can just sort of embed into your program. Yep. Oh, sorry.
The websites cannot be used for commercial purposes. Is that going to change?
So at the minute, this is a research project, and the main reason we say that is because we can't support, we can't provide the level of support for commercial use. But we have indeed plans to commercialize it in that direction. But at the moment, it's just a research project. I can't give any.
We can't say anything definitive there right now. Yeah.
Well, there's another question in the middle. Yeah.
So what's the current licensing if we can make it work? Can we include some of the stuff in a commercial project?
At the moment, unfortunately, it's just for trialing out the concepts. But if you are interested in using it in the commercial product, do let us know, because that will help.
And I think just to follow up from that, it's a great tool for prototyping, different probabilistic models. So certainly, you save a lot of time by using it, even if at the tail end, you would have to implement, a runtime. But hopefully, that it wouldn't come to that. I mean, as John says, you should contact us if that's something you want to do.
Yeah, what we're really after at this stage, being sort of at the research stage, is for people to use it and give us lots of feedback, and that will help us plan our strategy for where to go next.
Yeah.
Tough question. Change your concept for a minute of the Halo 3 scenario, and say that instead of one overarching score, you wanted to say, I'm going to give a player a profile, and I'm going to guess at their abilities or measure their abilities in a variety of different things. Have a variety of variables all double, and call this a profile for a user. And then let's say you observed an anonymous player playing, and you wanted to see if it matched one of those profiles. Can you see this inference engine working well to try and say, is that match true?
Yeah, absolutely. We've done that kind of model, that kind of program in other scenarios. What you'll find is, in this situation, you want to do something you want to learn very quickly, effectively, about a user. And if you have a lot of data about other users playing, then what you can do is you can say, effectively, that there are multiple classes of user that have particular sort of profiles of ability. And then you learn what those classes are from maybe 100,000 players or something that you have data for. And then when a new player comes along, because you've already done all of that learning, you only need to observe a few games, a few characteristics of that user to very, very quickly put them into one of these profiles. And you can use that in the gaming, but you can also use that in, for example, in adapting a user interface to people with different beginner, intermediate, advanced sort of levels of skill at using the software. So these are kinds of very ways of making these things bootstrap very quickly for new users. And you can certainly handle all of that within Infer.net.
And what kind of model do you end up using?
So a simple example would be, let's suppose we had users falling into those three categories, like beginner, intermediate, advanced. So you'd have an integer random variable with 3 values, integer. We actually support enum, so you could actually be beginner, intermediate, advanced. And you'd say if they're a beginner, you expect to see this kind of behavior. So you'd have like maybe a flow chart for the beginner behavior, a flow chart for the intermediate behavior, and a flow chart for the advanced behavior. And then you would say, okay, and infer which of these ones applied, and that would tell you whether they were beginner, intermediate, advanced with some probability.
So pick the highest probability and your set, right?
You can either pick the highest probability or sort of, well, I mean, that would be one way of doing it for sure.
Okay, I think we have to end there, but if there are any other questions, please just come up and ask us up here. Thanks.